With ray optics, we work with the idea that a single ray of light arrives at a single destination by bouncing off one point on a mirror. After all, Euclid's geometric law of reflection easily explains why we don't see light coming from any other reflection point. And this seems to be supported by Fermat's principle of least time. But how exactly does the beam of light know which path is the fastest path to the destination? Christian Huygens supported the idea that light is a wave. And as a wave, the reflected light may take almost any path to its destination, which seems to contradict both the law of reflection and least time. But we notice that when we examine the wave approaching the destination, the waves that follow the shortest path naturally arrive first. This means that all of the reflected waves cannot arrive in sync, with all the crests arriving at the same time with constructive interference. Some of the crests will overlap troughs and destructively interfere. This does not mean there will be no light intensity at the destination, but it does mean the result will be less intense than if all the light waves were synchronized. It also means that the strongest contribution to the reflected light received at the destination will be from waves traveling the shortest and fastest path. We know this is true because when we eliminate parts of the mirror which cause destructive interference, we measure a more intense amplitude at the destination. As you watch this animation, notice how the troughs of incoming selected reflected waves synchronize with the drawn red circles. The irony is that by removing some of the reflected light, we get more intense light as a result.